Yeah, I should have just gotten up and looked at him. And we got up at 5. Should have popped on because I was in the car. But we are where we are now, and it'll be okay. Hey guys.
Professor Tim, hi.
Hi.
I sent a PPT to you. Did you see?
Yep. I haven't gotten a chance to look at it yet, but I did see your email, and I will be reviewing that a little later today as soon as I have time. And then if you could come by my office hours, either today or Friday, we can kind of talk through your lecture and do a little practice run, make sure everything is how it needs to be. But I have not.
Can we make the other time, because today and Fridays I have to work?
Both today and Friday?
Yes.
Okay, yeah, just send me a time or give me a list of like 4 or 5 times when you could meet. And I will let you know which one of those I'm available for, okay?
Okay.
All right. Now what Yiping is talking about there, guys, is her student teaching. She's already chosen her topic for student teaching. 2.3, the limit laws section, is now taken. Let me just go ahead and show you the way I'm organizing this. So here's your class, and this is the one. So here's what we got. She chose to do section 2.3 on limit laws, which we're going to cover early next week. We're like almost ready for that now. So she and I are going to meet this week and do her little practice run. We're going to look over all of her materials and make sure everything is ready to rock and roll. I am hoping that I get the rest of these columns filled in for everybody over the next week. So please think about which section you want to student teach. I know it's a little bit tricky because right now we haven't talked about much calculus and it's hard to choose what you want to teach without any context, but flip through the book, right? Flip through the book, see which section looks manageable to you. I can give a few little hints here. Everything that I put in the syllabus, these are all pretty easy to teach sections. That's why I selected them as the ones I recommend for student teaching. Limit laws, limits at infinity, none of these are too bad. Sorry, that's my son. He's having a very excited morning. Section 3.1 on the power rule is not very hard at all. Section 3.2 on the product and quotient rules, also not terribly hard. Section 4.1 on mins and maxes. 4.9 on antiderivatives. 5.4 on indefinite integrals, and 6.1 on areas between curves. Those are the sort of especially tractable ones, the ones that are probably going to be the easiest to manage. So if you're having a hard time choosing, I would recommend maybe picking one of those, something like the power rule or mins and maxes or antiderivatives. Those are pretty easy to manage, and you'll be able to read ahead and start understanding those pretty soon. So like as soon as we've introduced the notion of a derivative, you'll be able to start prepping either of these or either of these. All right, so just make sure you send me your student teaching topic, your student teaching section, the section you want to student teach, and your honors project topic before the end of next week. And the sooner you do it, the more likely you are to get the one you want, right? Because this is a first come, first served thing. Okay, last time, let me first do the thing. So this is MAC2311. It is section OH1, the honors section, that is Calc 1 honors. And today is the 25th of August, 2021. Today, we're going to talk about limits. Well, really, I'm going to talk a little bit about something called topology. And then we're going to begin limits, which is section 2.1. And we may get to talk a little bit about section 2.2. But we'll take our time, right? So 2.1 is where we introduce the notion of a limit. I'm sorry, no, 2.2 is where we introduce the notion of a limit, sorry. So we're going to start on section 2.2. We're not going to bother with 2.1. 2.1 is a nasty distraction. So we're starting here. All right. And this is going to give us just a basic feel for what a limit is. And then Yiping on Monday is going to teach us concretely how to work with limits using limit laws. And then maybe Friday I will teach you guys the rigorous definition of a limit. We'll go over section 2.4. Okay, so first, topology. Comes from the Greek topos, meaning shape. So topology is the study of shape, really. It's a particular kind of geometry. The big concepts here are open sets and closed sets. And as you might have guessed from your experience with algebra classes, open intervals are open sets. Those are examples of open sets. But there are lots of other open sets besides open intervals. So what we mean by open we mean you can put a little interval, or you can put a little ball around any point in the set such that the whole ball is contained in the set. Now, the word ball in analysis has a particular meaning. It's the collection of all points some distance away from a specified center. Another way to think of open sets as a set that doesn't contain its own boundary. So when you go to do mathematics, specifically calculus, in a slightly more grown-up environment, we call it analysis. When you go to do analysis, the very first thing you need is a discussion of what's called point set topology. And that is precisely what we're talking about here. So let me show you an example of an open set. All right. In the plane, if I just take the interior of this blob, that is an open set. Because if you take any point in this set, so the dotted stuff is not included. All right, so the kind of dotted stuff here would be like the boundary of this set, and the interior, the stuff that is strictly inside that, is the open set itself. Because if you take any point in here, call it X, I can put a little ball around it so that that ball is completely contained in the set. No matter how close X is to that boundary, I can always do that because the boundary itself is not in the set. In other words, I know X is coming from the inside. In the real line, or on the real line, the prototype, or archetype, I should say, is an archetype. open set is an open interval. So let me draw for you an open interval. Here it is. All right, here's A, here's B. This is the open interval from A to B. And you see, no matter where I pick an element of this set, say like here, X, I can always put a little ball around that element that stays entirely within the set. The reason is because the boundary isn't included. If you tried to say this number right here, A, is in the set, then all of a sudden you would have a point, A, in your set, around which you could not put a little ball that stays in the set. So closed intervals don't have this property.
Question.
Mm-hmm.
I don't really understand the significance of this. Like, where have I understand these things better based on where I might have seen this before?
Yeah, definitely have not seen this before. Totally
Okay.
new concept.
Oh, okay.
So closed intervals, if you take your point X from the interior here, then you can put a little ball around it. But if you take your X to be one of these endpoints, then you're going to step out of the set with any little ball, no matter how small it is. So why is this important to us? This is going to connect in a deep way to the concept of a limit. Let me just finish the sentence here. Closed sets don't have this property because any open ball centered at either A or B will come outside of the set. All right. Why are open sets important? Why is this relevant to calculus? Because the whole concept of a limit is about studying the function's behavior on open sets, particularly on open intervals. The big concept I'm going to try to get through to you guys today is this intuitive picture of what a limit of a function is. And what a limit of a function is a pattern of the function's behavior on open sets. In particular, the big question we're going to try to answer today is, what does it mean to say that f of x approaches L as x approaches A? And so you can imagine in this setting, letting x kind of sneak up on A, getting closer and closer and closer and closer and closer to A without ever touching A. I don't care what happens at A, I care about what happens as x sneaks up on A. And that means I'm interested in the function's behavior on the open interval whose left endpoint is A. I'm not interested in what happens on the closed interval whose left endpoint is A, because this sort of sneaking up behavior doesn't really work there. All right. I would love to talk more about topology. I have a funny video about open and closed sets. Turns out open and closed are not mutually exclusive. You can be both open and closed. For example, the whole real line is open and closed. The empty set is both open and closed. One thing that kind of does make sense is that the complement of an open set is a closed set. So if you take the whole real line and you delete an open set from it, what's left will be a closed set. Or conversely, if you delete a closed set from the whole real line, what's left will be an open set. But this is, if you want to explore calculus in a more rigorous fashion, it's going to begin with a discussion of something called topology, which I just want to introduce you to the basic concepts of here, which are open sets and closed sets. Closed sets contain their boundary. Open sets do not contain their boundary. So your archetype of an open set is an open interval, and the archetype of a closed set is a closed interval. That's the sort of basics here.
Are you talking about the open set is A and B, those 2 points?
No, let me be a little more clear here. It's the things between those 2 points, not including those 2 points themselves. So the open set here is everything strictly between A and B, not including A and not including B. And then the kind of classic example of a closed set would be everything between A and B together with A and B themselves. So the archetype of a closed set is a closed interval. It turns out there are a lot of kind of interesting real world problems that just have to do with this thing called topology. One of them is the utilities problem. I'll share that with you really quickly before we move away and begin getting more concrete. The utility problem says this. If I have, imagine a 2-dimensional universe, right? Everything lives on a plane. I have 3 houses, call them house 1, house 2, and house 3. And I have 3 utilities, water, gas, and electricity. Is it possible to connect each house to each utility without any of the utility lines crossing? This is a fun topology problem. I'll call it a topology riddle. It's called the utilities problem. I have 3 houses. House 1, house 2, and house 3. And I have 3 utilities, gas, water, and electricity. Can you connect all 3 houses to all 3 utilities without crossing any utility lines? That's the question. So I could connect, the first house here to gas. I could connect the second house over here to gas. I could connect the third house over here to gas. I could connect the first house to water. I could connect the second house to water. I could connect the third house to water. But now I run into trouble with electricity, right? So if I try to connect this to electricity, that works fine. That blue is too similar to the other blue. I'll just use black. But now I'm going to have a hard time connecting house 2 to electricity without crossing over any of these other lines, right? I could get away with the first house here in this setup like this. But now how do I get this guy over to here? Can this be done? Turns out this is a problem that actually intimately relates to the concept of open sets and closed sets. And I'll let you ponder the riddle. I won't spoil it for you, but there is a nice solution. There is a nice answer to the question. So, topology and limits. the concept of a limit of a function is all about the behavior of that function on open intervals. In fact, as we go through this class and we develop more and more theorems, you'll start to see some consistency. Like every time I want to specify where a function be differentiable or have some nice property, I'm pretty much always going to require that those nice things happen on some open interval. Oh, David asked a good question. Can I connect the houses to each other? No, I want to connect each house directly to a utility. Everybody has to have their own meter, right? There would be other solutions to that, like in the real world, where you can get sneaky and subtract the metering out from one to the other. But here, just think of it as a toy problem where I want to connect each utility to each house directly. Okay. So let me just give you the intuitive definition. We say that the limit as x approaches c of some function f of x is equal to L, provided we can make f of x as close as we want to L by making x close to C. And you see, I put a few things in quote bunnies there because those are terms that have very specific topological meaning. When we talk about section 2.4, the rigorous definition of a limit, I will be very quantitative about what as close as we want means, or making x close to C means. For nice functions, this is kind of an obvious statement. So let me draw a nice function down here. What would be a nice function? How about the square root function? It's a pretty nice function. All right, so here's 1, 2, 3, 4. And here's 1 and 2. This is the graph f of x equals the square root of x. All right, and I'm going to pay close attention to the point here, 4, 2. I think we would agree. So here's the way I describe it to my non-honor students. I have a little guy walking along the graph, and his x value is going to get closer and closer to 4. Does his y value get closer and closer to 2 as he does that? So as the little man, or little person, walks along the graph, when his x coordinate gets again, I'm using the word close here in a particular way, gets close to 4, his y coordinate gets close to 2. All right, would we all agree? As I move this, which is his x coordinate, closer and closer and closer to 4, since he's walking along the graph, his y coordinate is going to get closer and closer and closer to 2. And the big idea here is that if you specify some distance from 2 that his y coordinate needs to be, I can find a corresponding distance that his x coordinate needs to be away from 4. All right, let me add a little bit more color here. Let me actually make this blue. And let me add one on the other side here. So here's what I want you to imagine. I want you to imagine this horizontal window here shrinking. And I ask, as this horizontal window shrinks, sorry, as this window here shrinks, does this window here shrink in a reasonable way, or does it jump around? Another way to say that is, if I shrink this window vertically, right? If I shrink these two closer and closer into their center 4, does the window here shrink down to 2? Now, this is a nice function. So the answer here is yes. Yes, it does. So by taking the x values sufficiently close to 4, I can guarantee that the y values will be sufficiently close to 2. So here we would say, I'm just going to plug into this expression all of the things that I have down here. That the limit as x approaches 2 of my function f of x, which is the square root of x, I'm sorry, the limit as x approaches 4 of my function, which is the square root of x, is equal to 2. As my x values get closer and closer to 4, my y values get closer and closer to 2. Really nothing magical going on there. In fact, if you plug 4 into this function, you straight up get 2. Turns out, having the limit be the same as what you get when you plug in, that's a very special property that we call continuity. You may have heard the word continuous before. That's how one defines continuity. Let's look at a less nice function. Oh, I'm sorry. Yeah, Sarah, you got a question?
No, sorry. One more time, how we would define.
I'm afraid your audio is breaking up quite a bit. Could you maybe type it in chat? David, I like your second idea, loop the utilities around the long way. Let's think about what the long way might be. And then I'm waiting to see Sarah's question in chat there, Sarah's comment in chat. Yeah, you can try that, David. You can try that. I encourage you to draw many versions of this picture. A whiteboard is useful, but if you don't mind going through the paper, do that too. It is. It is. There are things called winding numbers where we talk about rotating around. I think you'll find that you're going to run into problems however you try to loop them, unless you start changing the underlying space. So when you say go around the long way, if we were on, say, the planet Earth, which is round, you might mean go all the way around the planet. You'll find that you still run into trouble on a sphere. So if you start imagining that your planet is a little bit more donut shaped, you might find a way around this, or say coffee cup shape, which to a topologist, by the way, is the same as a donut because it's got a hole. But play with it. It's a really good problem, and it's fun to find the positive solution when you start allowing for different spaces. I haven't seen Sarah's comment here yet, so I am gonna push forwards a little bit. If we're able to get that into the chat, I'll be happy to come back and address it. So let's look at another example. So I'm going to do the same sort of thing. Only this time, really, save the tile, I'll fix it. Okay, here's a piecewise defined function. I'm going to say that the function f of x that I'm graphing here is defined piecewise to be the square root of x if 0 is less than or equal to x is less than 4. And it's the constant function 5 if x is strictly greater than 4. Don't worry about the algebra for now. We're going to come back and play with that in a minute. But I want you to imagine the same sort of picture where I take my little window from either side and I ask, as I start shrinking this window down here, does it shrink down over here or not? You'll see as I bring this left point closer and closer, then this horizontal line is going to, this blue dashed horizontal line is going to start coming up towards 2. But as I bring this guy in, he's always going to stay up here at 5. So as I shrink down like this, as I bring this in here closer and closer to 4, this piece up here just stays here. It doesn't come down closer and closer to 2. Another way to say that is if you imagine your little guy walking along the graph with his x value getting closer and closer to 4, his y value doesn't get closer and closer to 2. Right? In particular, as he comes in from the right, as he walks, if his x coordinate is to the right of 4, like it is here, as he comes in closer and closer to 4, his y value is just always going to stay 5. At some point, he's going to make a big jump down here. But in particular, his y coordinate is not getting closer and closer to 2 as he comes over from the right. As he comes over from the left, it would, right? Because from the left, this is the same function we were playing with a second ago. So as my guy walks along the graph with x coordinate getting closer and closer to 4, let me insert here from the right. His y coordinate doesn't get closer and closer to 2. From the left, it does. From the right, it does not. Here we would say, and I'm going to introduce some more notation. There's kind of two statements we can make. First is that if you look at the limit as x approaches 4 from the left, and this little guy right here means from the left, a little minus here. Of my function f of x. In this case, we do get 2, because as you sneak up on 4 from the left, your y values do sneak up on 2. But the limit as x approaches 4 from the right, and that's what that little plus means, that means from the right, of my function f of x, it's not equal to 2, right? As my little guy walks along the graph, getting closer and closer to having x coordinate 4, coming in from the right, his y coordinate stays 5. His y coordinate is 5 here, his y coordinate is 5 here, his y coordinate is 5 here. Exactly at 4, his y coordinate is 5. So here we would say that the limit from the right is equal to 5. So the kind of answer, what does f of x get closer and closer to as x gets closer and closer to 4, here depends on whether you're coming in from the left or coming in from the right. Therefore, I would not want to say, as x gets closer to 4, f of x gets closer to 2, because that's not always true. It depends on whether you're getting closer from the right or closer from the left. So in this case, we would not be able to say that the limit as x approaches 4 of this function f of x is equal to 2, or that the limit as x approaches 4 of f of x even exists. Because as I shrink the one window down, as I shrink this window down, as I bring these 2 points in closer and closer, it's not true that all the y values on the graph get closer and closer to any particular number. And this leads us to our first theorem, which kind of requires an understanding of one-sided limits. I'm going to take a look at just one more example here. Or maybe I'll go ahead and give you the theorem. Yeah, let's do the theorem. Now, we're not ready to prove this theorem yet because we need the rigorous definition of a limit in order to prove it. But here's the theorem. Well, I'll get it in your head so you can start thinking about it. The limit as x approaches c of f of x is equal to L only if both one-sided limits are equal to L. That is, the limit as x approaches c from the left of f of x is equal to L, and the limit as x approaches c from the right of f of x is equal to L. And I'll be able to prove this for you once we've covered 2.4 on that rigorous definition of a limit. But I think before we even try to approach that stuff, we need to get a better feel for the intuitive definition. So I'm going to look at a handful of other examples with you now. First, are there any questions on the terminology or the picture up here in this example? I want to make sure that we're really quite comfortable with this before I move on.
Is it possible I could meet with you at some point after class regarding it? Because my internet disappeared for a couple minutes and I think I just missed something.
Sure. Yeah, I do have an office hour this afternoon. And of course, we can talk there, or if you want, there's also the videos that are going to be up. We can do both.
Okay.
Let me connect this back to the topology thing for a minute. Notice that none of this argument cares which point is filled in. Right? Nowhere in this process did I refer to which point is filled in. In other words, I don't care what happens at 4. I only care what happens nearby. Over here, it's the behavior on this open set, which determines the limit from the left. And over here, it's the behavior on this open set, which determines the limit from the right. What happened exactly at x equals 4 has no bearing on the value of the limit or even whether the limit exists. And that's sort of the nice connection here to topology and open sets. Whether a function does or does not have a limit at a point doesn't give a shit about what happens at that point. It cares about what happens on open sets near that point. Okay, let's look at another example. So let me a function like this. We'll say this is the graph y equals f of x. Here, let me do something. Like this. Let's fill this one in. And then we'll come up over here again. And then do something. I'm going to draw a pretty exotic looking graph here. And then I'm just going to talk about one-sided limits at a few different points. Okay, and let's define this one right here to be this. Okay, so I'm going to call this height right here 2. I'm going to call this height right here 1, and then I'll call this 2, 3, 4, and 5. And we'll say this is the graph y equals f of x. Here's my x-axis. And I want to take these ideas and see if we can calculate the limits at 2, 3, 4, and 5. We're going to do that by looking at one-sided limits for each of them. Alrighty. So let's see if we can find the limit. No. The limit as x approaches 2 of f of x. The limit as x approaches 3 of f of x. The limit x approaches 4 of f of x. And then finally the limit as x approaches 5 of f of x. And at this stage, everything is coming from the picture. You're not expected to do any quantitative work, really just qualitative work. So we're asking in each of these cases, as x gets closer and closer to this input, does f of x, the output, the y value, get closer and closer to any particular output? All right.
Is equal to 2.
Very good. This first one, the limit as x approaches 2 of f of x is equal to 2. Could you explain why?
Because the graph from the 0 to 2 is close to is approach to 2, and the horizontal y-axis is close to 2.
Yeah, that's a sound explanation. So if you imagine, I'll put it in terms of the picture that we were talking about. If you imagine a little guy walking along this graph, as his x coordinate gets closer and closer to the input 2, his y coordinate is getting closer and closer to the output 2.
And also the right side close approach to 2, and the y axis is close to 2 too. Both ln x approach 2 minus f of x is equal to limit x approach 2 plus f of x. They have the same behavior, so it's 2.
That's exactly what I was just about to say. So Yiping's answer here is correct. This is equal to 2 because whether I'm coming in from the left or coming in from the right, as I walk along this graph with my x value getting closer and closer to 2, my y value is getting closer and closer to 2. So no matter which direction I come in, from the left or from the right, my y values are approaching the y value of this hole. So the way we'd say that is because the limit as x goes to 2 from the left of f of x is equal to 2, and the limit as x goes to 2 from the right of f of x is equal to 2. That's the idea. Now, what is f of 2?
One.
It's not, yes, it's 1.
Very good, right? It's down here. It's coming from this point. So f of 2 itself is equal to 1. Why would we not say that the limit is 1 then?
Because the limit is not actually the number itself, it is the infinitely close to the actual number.
That's true. That's a correct statement. If I tried to claim that this limit was 1, how would you argue against me, specifically using the rules and concepts we have related to limits? And what David said is correct there also. It's kind of equivalent to what William said. We don't care what happens at 2. We care about what happens nearby, right? And if my x values are really nearby 2, then my y values are way up here. They're not anywhere near this thing. They're not getting close to this thing. They're fucking way away. So that's the big idea here, is that as we bring our x values in closer and closer to this x value, our y values are getting closer and closer to this y value. this point here might as well be 1,000,000 miles away because I cannot shrink in on that point, right? You see, as I shrink these two things in towards 2, these two vertical lines will also shrink in towards 2. They're not getting anywhere near this guy. All right. Let's look at 3 next.
Sorry, could you explain that? I feel like I really didn't understand what just happened.
Okay, so we're asking, what does the function f of x do as its input gets closer and closer and closer to 2?
Oh, so that bit, that first bit I totally understood. When you started going f of 2, that's where you lost me.
Okay, well, remember f of 2 is the y value on the graph of f of x when the x coordinate is exactly equal to 2. And because I have an open hole here, it's not this y value. There is no point on the graph right here. The actual point on the graph is down here at y value 1. So f of 2 itself is equal to 1, which is different than the value of the limit. So let me draw another picture here. I can make this really concrete. Consider the following function. The graph of this function looks like this. F of x, the output is equal to 1 if x is not equal to 0, and it's equal to 0 if x is equal to 0. So if you want to plug in some points like f of 1, well, 1 is not equal to 0, so f of 1 would be 1. F of 2, 2 is not equal to 0, so f of 2 would be 1. F of -1, -1 is not equal to 0, so that would be 1. F of -2, -2 is not equal to 0, so that would be 1. Right, that's all of these points. But right there at 0, we can go even a little further here. I would say f of 0.1 is equal to 1. F of 0.01 is equal to 1. F of -0.1 is equal to 1. F of -0.01 is equal to 1. Because all of those inputs are not equal to 0, all of their outputs would be 1. But f of 0 itself is 0, right? Because that's the way the function is defined. So in other words, this is a function whose graph has a hole at one point here, right at 0. Everywhere else, the function is defined to be 1. So this is another case where if you were to look at the limit, as I sneak up on 0 from the left or sneak up on 0 from the right, in both cases, my y values are always 1. So here we would say that the limit as x approaches 0 from the left of f of x is 1, and that's the same as the limit as x approaches 0 from the right of f of x. So we would say that the overall limit does exist and is equal to 1. However, the actual value of the function there at x equals 0 is 0, because that's how the function is defined. It's defined to output 0 when you feed it the input 0.
So my question, I suppose, would then be, why is it just a blank space? Why doesn't the line just dip down to 0?
Oh, well, because this is how the function is defined. Right? We started with this definition of the function, and then we're asking what kind of properties does this function have? I could define another function that dips down and then dips back up, sure, but it wouldn't have this definition. It would have some other definition. Does that make sense?
Not really. I'll just ask later, I guess.
All right, this is coming from piecewise functions, which may be something that are worth reviewing. I know not every pre-calc class spends the time they should on piecewise functions, but let's return to the example at hand.
Cool. Thank you.
Of course. Okay. going on at 3?
Undefined.
Yeah, I would say that this limit fails to exist. The way you're going to write this usually is as DNE, does not exist. It's a little bit weird to say equals DNE. You can just say that limit does not exist. Because as you shrink your window about 3, as you bring it in from the right, you're watching these y values, which are getting closer and closer to 2. But as you bring it in from the, as you kind of do it like this, yeah, as you bring it in from the left, you're watching these y values, which are getting closer and closer to something down here. Like, we'll call this -1. So this we would say does not exist because the left limit, the limit as x approaches 3 from the left of f of x, that's coming down here towards -1. But the limit as x approaches 3 from the right of f of x is up here. It's getting closer and closer to 2. And if the left limit and right limit are not equal, then the overall limit does not exist, right? We cannot say that that function value is getting closer and closer to any particular number as we shrink in from both sides. Again, here it's fun to ask, what is f of 3? So what is f of 3 here?
-1.
Very good. F of 3 is -1, which happens to match this limit. And the term for that, we would say that f of x is, I would say this function is continuous from the left at x equals 3. And we'll talk more about what continuity really means, but sort of the idea is that as you sneak up from the left, you do get the function value. But as you sneak up from the right, you get something else, which is not the value of the function at 3. The next thing I want to look at is what goes on at x equals 4. And in this case, we have a vertical asymptote. So as my x values get closer and closer to 4 from the left, let's look at the one-sided limits. Those y values, this just goes up and up and up and up. Those y values, yeah, we would call this positive infinity. And as x approaches 4 from the right, we're diving down. So I would say that that is negative infinity. So here again, we would say that this limit does not exist. Because negative infinity and positive infinity certainly aren't the same thing. Not on the real line, at least. The last one I want to look at is what's going on at x equals 5. And I don't quite have room to show the space down here at the same time. So I want somebody who I haven't heard from much today to tell me what's going on at 5. As x approaches 5, what is f of x doing?
Limited x approach 5 is equal to 0.
That's true, yes. So if you imagine a little guy walking along the graph with his x coordinate getting closer and closer to 5, coming from either direction, his y coordinate is getting closer and closer to 0. And the logic again is the same.
Does it matter that actually, like, at the value of x is equal to 0, then it's going to be like the coordinate 0, 0.
Well, 0, 0 is over here. So
Sorry, yes, but would it matter that like it's an actual point on the graph?
no, it doesn't. And that's a really good observation. So if this was an open hole and then I had the filled in point up here, that would not affect the value of the limit. That's kind of like what we see here at 2, right? Where the point on the graph and the value of the limit are different things. All right, because the limit as x approaches 5 from the left of f of x is 0, and the limit as x approaches 5 from the right of f of x is also equal to 0. So these are kind of the basics of limits. We want to understand the fundamental concept behind a limit. We should think about it intuitively first. And just like Kalia said, the value of the function at the point there really doesn't matter. That's not what determines the limit. In each case here, what's determining the limit is how the function behaves on an open set centered at that point. It's not what happens at 2 that determines the limit here. It's what happens nearby 2, just to the left of 2 and just to the right of 2. It's not what happens at 3 here that determines the limit. It's what happens nearby, just to the left and just to the right. It's not what happens at 4. This function isn't even defined at x equals 4. It's what happens to the left and to the right. And the same is true at 5. So this is the sort of deep connection between topology and limits. In order to talk about a limit, you need to be comfortable with this idea of an open interval and sneaking up on a point from the left, sneaking up on a point from the right. And what we're doing is basically just puncturing the x-axis. I'm plucking 2 out here. I'm saying, I don't give a shit what happens right here. I just care about what happens very, very nearby, very, very nearby. Okay. There are some other ways that a limit can fail to exist. There's sort of 2 things that I want to show you before I let you go for today, in addition to this. The first is a sort of wild oscillation. And there are many examples of this, but the classic is the sine of 1 over x. We know what sine x looks like. Sine x is just a wave, right? It's a wave with amplitude 1, and it's periodic with period 2 pi. But sine 1 over x is very different. You see, as x gets smaller and smaller, 1 over x gets bigger and bigger and bigger. So what's going to happen here the function will be reasonably well behaved. Reasonably well behaved as long as we stay away from 0. And this oscillation will kind of decay. But then as you get in close here, he's going to start bouncing back and forth very, very quickly. And then he'll start to oscillate more slowly as you go further away. Let me show you in Desmos, because this is kind of a hard thing to draw. There it is. So imagine you're that little guy walking in on this graph, and you're letting your x coordinate get closer and closer to 0. See if I can track this actually. T, comma. Insert a slider. 1001 will let me do this. Let's see. Yeah, here we go. No, still not letting me do it. All right. So imagine you've got a point, your little guy, and he's walking in, trying to get closer and closer to 0. That is x coordinate closer and closer to 0. As you come in here, he's going to start bouncing back and forth really violently. And play with the scales a little bit. Let's just do from 0 to 0.01. All right. Here's as good as I can do for you. As x gets closer and closer to 0, you see this point bouncing back and forth wildly. The graph actually becomes, the term here is dense, becomes dense in the plane as x gets close to 0, because those oscillations get so friggin' fast that we really can't keep track of them anymore. So would it make sense to say that as x gets closer and closer to 0, these y values are getting closer and closer to any particular number? One way to check this is to imagine you have some number. That would be that limit. Your y value is going to bounce back and forth from being close to that value to really far away from that value infinitely many times as x gets closer and closer to 0. So forgive my bad art here, but when a function's output oscillates, 2L oscillates infinitely quickly near a particular x value, it's very hard for the limit of that function to exist at that x value. And now I'm saying very hard because it's actually not impossible. I can show you an example of a function where this does work. Rescale. Here's an example of a function that still oscillates very, very quickly near 0, but those oscillations are getting smaller and smaller and smaller. Here's another example. These oscillations, they are getting very fast, but they're also getting very, very small in their amplitude. But if you just have something like this, then there's no saying that this function's value is approaching any particular number as x gets closer and closer to 0. This is one of those special cases that's a little bit hard to wrap your head around at first until you have the rigorous definition of a limit. And that's what I'm going to leave you with here today, is the rigorous definition of a limit. And next time, we're going to begin class by looking at this function, sine 1 over x, and seeing why it's not possible for it to have a limit at 0. So this is actually section 2.4. I'm going to pick it up here on Friday to see exactly why sine 1 over x can't have a limit as x approaches 0. We need a rigorous definition of a limit. So remember at the start of class today, when I defined what a limit was, I said it's an intuitive definition, right? As you get closer and closer, the y values get closer and closer. Here is the rigorous definition. We say that the limit as x approaches c of f of x is equal to L, provided for every positive number epsilon, we can find another positive number delta such that if x minus c is smaller than delta, then the absolute value of f of x minus L will be smaller than epsilon. That's the idea. And the picture that kind of goes with this this. Let's say here is my C. Here is my L. You kind of pretend like God gives you epsilon. Something beyond your control picks the number epsilon. And they specify an epsilon window about L. As carefully as I can here. And then it's your job to find the corresponding delta window. About C. So this would be C minus delta, and this would be C plus delta. What we want to do is find delta so that if x is within delta of C, in other words, if x is anywhere inside the purple, then the corresponding y value, f of x, is within the blue epsilon window. That's your task. That's how you prove a limit exists. So you pretend like there is some unknown positive number epsilon, then you create an epsilon window about your suspected limit L, and it is your job to find the delta window about C that keeps f of x within that epsilon window as long as x is within the delta window. This is how you say it algebraically. Don't be intimidated by the Greek letters. If you want to replace them with D's and E's, you can do that. But you know, it's fun to learn new stuff, right? So this is a lowercase Greek delta. This is a lowercase Greek epsilon. And this is what we're going to work with starting next time. Right? I will prove for you a few very simple examples, and then I'll prove for you that sine of 1 over x could not possibly have a limit at 0 by showing that any reasonable choice automatically fails this definition. But this is the definition that we're going to work with. And I do want you guys to try and come to understand this. It's a little bit tricky. You may want to Google between now and Friday so that you have a little bit of experience with the terminology and absolute value stuff before then. That's all I have for you guys today. make sure that you're starting to work on that homework. We now do have some concept of what a limit is, so you can get in there and start working on that. If you get stuck on anything, come see me in office hours or send me a Canvas message. And then on Monday, make sure everybody shows up here on time and is nice and polite, as Yuping very bravely does the first student lecture for the semester. I'm confident everything will go well, but let's just remember to all show her the same respect you would show me or anybody else. Is there anything you'd like to ask before we wrap up for the day?
Professor John, please give me some times, make an appointment.
Yeah, the easier thing to do would be for you to send me sometimes, and I'll let you know which ones work for me, because my schedule's kind of all over the place. So just send me like a list of 5 times that would work for you, and I will pick one and then send you a Zoom link. Does that sound okay?
Okay.
Okay, very good. Is there anything else? I see there's some things in chat here. Let's make sure we. Time just shows me the books. So Daniel's asking, how do we access the homework? You do have to go to WebAssign. You have to put in your class key and then select the register for our class. If you have an access code, you'll need to put that in. I know that WebAssign's having some trouble. A lot of students have been complaining about not being able to get in. Try refreshing the page, try using a different browser. If all else fails, I do have, I think I shared this with the class the other day. Anybody having trouble?
If I may, I found that when I copy pasted it from Canvas, it never worked, but when I retyped the exact same thing from scratch, it worked, no problem.
That's
For as
interesting.
far as the class code.
I do know some people have had trouble with, is it here? Here. There's a space here that's going to automatically want to copy with the number. Make sure that you don't have that space at the end. You should be able to copy paste, but if you're having trouble with that, try typing it. That seems to be working. Yeah, you definitely need to include SF College. So the bold stuff, just the bold stuff is what you need there. But take a look at the chat above David's there, the one that I sent at 12:18. If you haven't registered for WebAssign yet, please just copy that into a notepad document. So if you do have trouble registering, you can join this meeting with the Cengage people and they'll step-by-step walk you through it. Yeah, they've been making a lot of changes to the API. It's annoying. I'm not a fan, but we'll get used to it. Daniel asks, do I need to purchase access first? No, you do not. You can get in with a temporary access. You don't need to have purchased your access code yet. All you need is the class key. But you will need to purchase an access code within the first 2 weeks, otherwise they will kick you out. Let me see anything else. Okay, yeah, and also, what does the arrow mean? Sorry about that. I forget this is not a logic class. This means implies. So A, big right arrow B means A implies B, which can also be read as if A is true, then B must be true. So what we're saying here is that for every positive number epsilon, I can find a positive number delta such that if the absolute value of x minus c is less than delta, it is necessarily true that the absolute value of f of x minus L is less than epsilon. In other words, if x is within delta of c, then f of x will be within epsilon of L. Alrighty. Where do you put in the access code? As you go through the registration process, it will ask you for an access code. If you don't have one yet, you'll scroll down and look for a link that says use temporary access. Honestly, I haven't registered myself as a student in WebAssign with this new API, so I'm not sure precisely what it looks like. But it should ask for the access code at some point. Daniel, I would recommend then going to that Zoom meeting that I posted up here. Either follow this link, which I pasted in the chat, or open Zoom after class and put in this meeting ID. And that'll take you to a little help session that Cengage is running. If you've put in the class key and it says you're registered for this class, then you should have access. But I know that there have been some browser issues. You may need to clear a cache or something like that. Possible places to buy WebAssign access codes include the campus bookstore. And if you're going to use your financial aid chart, like you want to charge it to your financial aid, that's the only place. Amazon has them. You can buy them directly from Cengage during the registration process. It costs around $100 direct. If you're lucky, you can also try to scoop them from, like I said, Amazon, Abe, other third-party sellers, sometimes resell unused ones. But the two kind of most convenient would be direct from Cengage or from the Santa Fe bookstore. All right, nice to get these questions sorted out. Anything else that we'd like to ask about before we get scooching?
Quick question.
Yeah.
So it's something that a couple of professors have all been sort of focusing on. So generally, what would you recommend we have done before each class to do well in that class?
The homework that is due that day. So like for Monday's class, I would make sure that you have done the homework that's due on Monday. For Friday's class, I would make sure that you've worked your way through a bit of that homework. Let me take a look and see. I can give you a problem number to shoot for.
Oh, that'd be fantastic. Thank you.
Yeah, let's do that. I don't think I put any 2.4 stuff in there, or 2.6 stuff. So probably you could do all of the homework by now, but I would want you to work a significant enough portion of it that you started to develop some intuition. So let's take a peek.
And when I'm on WebAssign, it showed me, sorry, it showed me there was like an option that said current homework assignment. I should always be able to just generally trust that if it's saying that that's current, that's the current.
I'm not sure. Yeah, like I said, the new API from the student end, I have no idea what that looks like. But if it's displaying an assignment as the current assignment, then probably that's the one you should be working on, unless one has gone by that you need to make up from the past.
Yeah.
I would say, especially if we want to work on piecewise functions, try to knock out at least through problem 10 by Friday. And then the remainder of these, yeah, let's see. Let's see. This is a 2.3 problem, isn't it? Yeah, okay. I may have to extend this because we're not going to do 2.3 this Friday. Like I know we're going to do it on Monday. Yeah, so try to get up through problem 10 done by Friday. That would be a good target.
Okay.
And then we'll
Sounds
talk about everything you need for problems up through 16. Really, you could go up through 16 if you wanted. Problems, I'm just seeing this now because normally I do 2.3 in the first week, but because that is Yiping's student teaching, we won't actually cover 2.3, even though there are some 2.3 problems in here. So some of this problem 21 and beyond, I wouldn't actually expect you to do until after Yiping's student teaching. So I may split this up a little bit. We'll talk more about it on Friday.
Okay, sounds good. Thank you.
No problem, gang. Anything else before we go?
That should do it.
This
Thank you.
this one, we say limit x approach c f of x is equal to L. Provide for every what's this?
Epsilon?
Epsilon greater than 0, we can find delta greater than 0. I cannot understand here.
Such that.
Such that this one, so it means I saw you draw the graph. X is X is at the X point, that y-axis is f of x, and the C point is equal to L. FC is equal to L, right? L.
It is true here that f of c would be equal to L, but that wouldn't necessarily need to be the case. Remember, this could be an open hole and I could have the point up here and the definition would still be satisfied.
Okay.
So the real idea is that as this epsilon window shrinks, this delta window also shrinks. And no matter how small this epsilon window is, I can find a corresponding small delta window that will guarantee any x within this interval down here gives me an f of x that is within this window over here.
Hmm.
Right, so I think the first thing to do is to practice with the easy intuitive problems in the homework. And then the next approach is going to be to break this apart algebraically. I'm going to show you guys how to actually manipulate statements like these, and then to try and make the connection to the picture down here. So first, practice the easy problems. Then on Friday, I'll show you how to play with this sort of stuff. And then on Friday also, I will connect that to this picture here. Does that sound okay?
Yes, it sounds good. Thanks.
All right. Sounds great. I do see some advice from Nikita here. On the left side, there should be something that says course. Click the class, then you should see it. So if you're having trouble finding the course in WebAssign, but you've already registered, look on the left side of the page for something that says course. Otherwise, just go to the Zoom meeting that I posted the information for there. And that is it. That's all I've got for today, guys. So I'll see you all on Friday.